We're going to be graphing exponential equations today, and exponential equations have lots of applications in lots of different fields. Yes, in physics, but also in economics, business, biology, demographics, population growth, and all that kind of stuff. So, and we're going to be looking at a very special kind of exponential function. But let's start off with a very, very easy and general example of an exponential function, and we'll graph it, and then we'll look and we'll get more and more specific. So let's take a look at this. Y equals 2 to the x power. And this is pure math right now. Could you turn the lights on for that side? Thank you. So here's what makes this an exponential function. Y is a function of x, but x is in the exponent of this number. And that's what we mean by an exponential function. So let's graph this. And so we'll pick some values of x and some values of y. And let's just go 0, 1, 2, 3, and 4. That'll be good enough. And so let's plug in 0. What is 2 to the 0 power? It's 1. You don't always do that. So this is y, and so this would be 1. And what is 2 to the 1 power? What is anything to the 1 power? Itself. Pretty easy so far. And then what is 2 to the 2 power? What is 2 to the 3 power? What is 2 to the 4 power? 16. And if we graph this, well, 0 to 4, so 1, 2, 3, 4. And then 1 to 16, so let's see, 1, 2, 3, 4. This is just some x. And we'll go 5, 10, 15, 20. So this is y. So at 0, we'll start at 1. So it doesn't start at 0. It starts at 1. When x is 0, y is 1. And then it's 2. So let's look about 2 right there. And then at 2, it's 4. And at 3, it's 8. And then at 4, it's 16. Okay. So it looks like it's got a nice, smooth curve like this. Of course, what if I went 5? Okay, it would double again. Notice that we start at 1, and then we double 1 to 2, and then we double the 2 to get 4, and then we double the 4 to get 8. We double the 8 to get 16. We would double the 16 to get 32. So it'd be way up here somewhere. So it would just continue. And it's got a very steep. So this is an exponential curve. Okay, now let's do this again, but for a little bit more complicated function. This time we're going to multiply it by a number up front, and then we'll use 2 as our base of our exponential function once again, but I'm going to put negative x right there. So 5 times 2 to the negative x power. So x, y, and we'll just pick the same numbers, 0, 1, 2, 3, 4, maybe we'll do 5. And this you really don't need a calculator for because, well, maybe you do. Maybe we do. I don't know. Let's put in a 0. What is 2 to the 0 power? 1. And what is 1 times 5? It's 5. You have to remember to multiply by the 5 now. And then what is 2 to the negative 1 power? What is it? That's 1/2, isn't it? And so, so what is half of 5? 2.5, right? Okay, and then we're going to make x equal to 2. So I'll actually show the work here. This is 5 times 2 to the negative 2 power. Now what does that actually mean? It's 5 times 1 over 2 squared, or which is 1 over 4. So what is 5 divided by 4? 1.25. But you could have gotten that by just taking 2.5 and dividing it by 2. And then we do the same thing here. Y equals 5 times 2 to the negative 3 power. Well, that's 5 divided by 8. And that, if you get a calculator out, is 0.625. And then 4. Well, that's 5 divided by, well, I'll double that's 16. And that should be 0.3125. And then this finally, y equals 5 times 2 to the negative 5. Well, what is 2 to the 5 power? That's 32. So 5 divided by 32. So 5 divided by 32. And that's, well, this divided by 2. Now I could probably round those off. But see, the graph here is very different than the previous graph. Here, in the previous graph, this power of x was positive, and so it was getting greater. But these are getting smaller. So if I was to graph this, zero, 1, 2, 3, 4, 5. And then this goes from, well, 5 to almost 0, so we'll just do this 1, 2, 3, 4, 5. And we'll graph it at 0. We have 5. So we're starting off with our maximum value. And when x equals 1, we've got 2.5. And then 2, it's 1.25, which would be right about there. And then at 3 seconds, it's 0.625, be right about there. And then at 4, it's, well, it's half of this, 0.3125. And here, where it's half as much again. And here we've got a nice smooth curve as well. But what is this curve getting closer and closer and closer to? So what, yeah, I mean, is y ever gonna be 0? No, but as x gets really, really big, y gets really, really close to 0. Really, really close to 0. Okay? Anybody have questions on how to graph these things? Okay, well, now we're going, yes?
Are we going to find the slope of
No. We're not going to deal with the slope of this. You would in a calculus class. Yeah. Okay. Now I'm gonna take a leap here into something that is a little bit different, and now you have to use your calculator. Let's say that instead of using the power of 2, we're going to use the power of e. We're going to say that y is equal to, let's just make one up. 3 times e to the x power. And so here we're multiplying by something, and here we've got the exponent. And here we'll just do 0, 1, 2, 3. That'll be good enough, because this is going to get really big really fast. So e is a number, right? E is an irrational number. And here's, well, first let's figure out what y is when x equals 0. What is any number to the 0 power? 1. 1 times 3 is 3. But now, what is e to the 1 power? What is anything to the 1 power? Itself. And I want you to be able to do this. So here's my calculator. Let me zoom in on it. Now, my calculator is different than yours, probably. So you're going to have to figure out where to find this and how to do this on your calculator. But here's mine button, and usually it's associated with the natural log or ln button. And here you can see right here is the e to the blank. It has a little blank above it. So if I want to find e to the blank, I'm going to have to hit the shift button and then the natural log button, but it's actually giving me that. Okay, so let's clear this. So I'm going to say e to the 1 power. So I'm going to go shift e, and I get this little e to the blank, and then I just press 1, and then equals. And look what I get. 2.718281828. That is e. It's an irrational number. It's a little awkward to use. You have to use a calculator or you can drive yourself crazy. Okay. But what am I taking this number and doing? So e to the 1 is e, but then I'm multiplying by 3. So what this is this times 3 equals, and I get 8.15. We'll just round it off to 3 significant figures. And then we'll do 2. So now I'm going to go e to the 2 power. And what do I get? I get 7.38. That's e times e is 7.389. Then I'm going to multiply that by 3. And I get 22.2. Again, rounding off. And then 3, well, that's e times e times e, which is a lot easier just to go e to the 3 power. And then multiply that times 3. And I get 60.3. So look how fast this thing is getting bigger. We start off with 3, we get all the way up to 60 in just like 1, 2, 3 powers of x. So, and that's expected. So let's just draw a real quick sketch of this. So 0, 1, 2, 3. this is x. And here we've got to go all the way to 0 to 60. So I'll go 10, 20, 30, 40, 50, wait, 10, 20, 30, 40, 50, 60. So 20, 40, 60, and this is y. Now, where would 3? Here's 10. 3 would be way down here. It's not at the 0, though. And then 1 is at 8.15, which would be somewhere right there. And then 2 would be 22.2. And then 3 would be 6. It's really big, 60.3. And so we see a curve, again, that's getting greater and greater and greater. So that's an exponential function. Oh, no, I was on screen. Okay, so let me zoom out a little bit. Okay. So this is all fine and dandy. Now we're going to take a leap in complexity. We're going to do the same kind of thing here, but we're now going to be using this to model something real. In this case, temperature. Let's say the final temperature is equal to some initial temperature, 200 kelvins. The K stands for kelvins. Times e to the negative t. Oh, what did I? This is the wrong one. Over, and we'll make this 2 seconds. Okay, now we made this a little bit more complicated, but I want to point out some things to you. If we're measuring temperature in kelvins, well, let's pick some values for T. Now we're dealing with quantities that have units. This is temperature in kelvins, and this will be time. Oh, let me put them in the right order. Sorry. Usually go X, Y. So this will be time in seconds, and this will be temperature in kelvins. Now, take a look at this. When time is 0, that means this power of E is 0. So E to the 0 power. I know there's a negative there, but it's just negative 0. It's just 0, right? What is E to the 0 power? 1. And what is 1 times 200 kelvins? 200 kelvins. So really, this right here is the temperature when time equals 0. And we're going to do a lab where we're going to measure temperature and see how something cools off or heats up. But this is the temperature that you start with. It's your starting temperature. Now, let's just put 1 second in there. And here's what I want you to see right here. Well, let's actually do the math here. 200 kelvins times e to the negative 1 second divided by 2 seconds. Okay, so what do I get? This is equal to 200 kelvins times e to the negative 1/2. E to the negative 0.5. Does everybody agree with that?
Yeah, it does.
And what did you get?
121.3.
121.3 kelvins. And I want to show people that using the calculator here, how you type that in. I usually do the exponent part first, so e to the negative 0.5 equals 0.606, and then I multiply that times my starting temperature, and you get 121.306. Okay. Now let's put in let's do 2 seconds. So if I put in 2 seconds for time, I get e to the negative 2 seconds divided by 2 seconds equals e to the negative 1. So shift e, and try to follow along with the arithmetic as I do this. Go e to the negative 1 power. And you get 0.3678794412 times my starting temperature. And I get 73.57. Did you get that?
Yeah.
Now, one thing I want to point out to you is this. I haven't talked about it yet, but look at this exponent right here. And look at this. Let's look at e to the negative t over 2 seconds. Why do I have this look at this thing right here. This has a name. This is a very important thing. So everybody pay attention right now if you fade it out. This 2 seconds right here, this is called the time constant in an exponential function. And we're going to be, all the exponential functions we're going to be dealing with are functions of time. So this right here is called the time constant. And you need it. You need a time constant in order to make the math work. Because look at this right here. This right here is an exponent. E to some power. What has to be true about this? I'll just call it x. What has to be true about that exponent of e? It can't have any units. It must be dimensionless. What is 2 to the 3rd power? What does 2 to the 3rd power mean? Okay. It means 8, but what is this 3 telling you to do? Right? It's how many times you multiply it by itself. What if this was 2 to the 3 meters? What? What? No, it doesn't make any sense. This is stupid. Okay? It has to be a counting number. And it can be a fraction, or it can be a decimal number. That's okay. But it can't be anything with units. So if I'm plugging in time into this exponent, I've got to cancel out the seconds somehow. And so I have to have something in there called a time constant. So this 2 seconds right here is a time constant. We give it an abbreviation, tau. Tau is a little Greek letter, and you'll see it when you're dealing with exponential functions. And it's just something you have to divide the time by in order to make this a real exponent. And the time constant does have an effect on what the graph looks like, obviously. It tells you how fast or how slow the graph curves as time goes by. Okay.
Real quick.
I'm recording, so.
Okay, yeah. Okay, so tau, the time constant, is also the time required for the graph to go to 1 over e, okay, which is roughly, you're losing about 63% of your original value. So that's also what that means.
And so if we go here, let's do 3 seconds. So we're going to have, well, actually, you know what I'm going to do? I'm going to do multiples of tau. So let's do 4 seconds. Let's do 6 seconds. And let's do 8 seconds. And that'll be enough. So what is 4? Just all you got to do is plug 4 in there. What is 4 divided by 2? 4 seconds divided by 2 seconds is 2. So we're going to have e to the negative 2 times 200. Do it for 6. Now here's why I'm doing multiples of tau, because it makes it easy to graph. Here's 2 seconds is my time constant, so I'm just going to graph like 5 different multiples of this. So 6, what is 6? 6 seconds divided by 2 seconds is 3. So it's going to be e to the negative 3. And times 200. 9.957. And then 8 divided by 2 is 4. So e to the negative 4 times 200. 3.66. Oh, we'll do one more. 5 taus. I want 5 tau. What is tau? 2 seconds. What is 2 seconds times 5? 10 seconds. So we'll go out to 10 seconds. 5 tau. All right. And so plug it in. 10 divided by 2 is 5. So that's e to the, e to the negative 5 is very small, and then we're going to multiply that times my starting temperature. Very, very small value. And we'll stop there. Now I'm going to graph this. But now this is time in seconds. And we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then let's look at the vertical scale. Well, we'll go from 200 to something that's really close to 0. So we'll just go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 50, 100, 150, 200, temperature in kelvins. And now I'm going to graph it. At 0, it's 200. So it starts off at its maximum. Now, I'm just going to skip this one. I'm just going to go to 2. At 2 seconds, it's 73. So it's dropped quite a bit. 73, it's right here. And then at 4 seconds, it's dropped quite a bit, and it's already down to 27. And then at 6, it's all the way down to 10. And then 8, it's almost not even visible up there. And then it's 1.35 on this scale. It'd almost be practically right on the line. So here we have this very, very famous curve. Now, let's go ahead. We can put the 1 second in there. It should be 1.121.3. Well, let's see. 121.3. Woo, look at that. That's nice. Now this is called exponential decay. And this is going to describe how things cool off. So, but I want to give you some practice with it. Okay. And one thing to notice about this, one thing that's true about all exponential decay functions anyway, see how this is shrunk down? Look at the fraction of this compared to the whole thing. It's about a third maybe. Actually, it's a little bit less than a third. No, a little more than a third. Was it 0.38? Something like that. Now look at this one. To go from here to here, you go down by the same fraction. To go from here down to here, you go down by the same fraction. Each time you go the same amount of time, you go down by the same fraction. And that's one thing that characterizes an exponential function. It either increases or decreases by the same fraction each period of time. There's one other function that I want you, that's very similar to this, that I want you to be able to graph and see. Now I'm going to take the same graph we had, or the same function we had almost. T equals 200 kelvins. But now we're going to go 1 minus e to the negative t over 2 seconds. And we're going to graph this now. So this is going to be time in seconds. This is going to be temperature in kelvins. But it's gonna look like this. Well, let's put some values in here. What is our time constant once again? 2 seconds. So what I'm going to do is go multiples of 2 seconds. 0, 2, 4, 6, 8, 10.
We're totally going to interrupt your class right now.
Well, I'm recording, but that's okay. All right.